joint meeting of task 1.3 and task 1.4. We have the invited speaker, Prof. Dr. Pascal Hitzler. Pascal Hitzler is university distinguished professor and endowed Leot T. Smith Gravity in Engineering chair at the Department of Computer Science at Kansas State University, one of the directors of the Institute for Digital Agriculture and Advanced Analytics, and director of the Center for Artificial Intelligence and Data Science. Until July 2019, he was endowed NCR Distinguished Professor, Rage Golding Distinguished Professor of Research, and Director of Data Science at the Department of Computer Science and Engineering at the Wright State University in Dayton, Ohio, USA. He is Director of the Data Semantics Days Lab. His research record lists over 400 publications in such diverse areas as neurosymbolic artificial intelligence, semantic web, knowledge graphs, knowledge representation and reasoning, determinational semantics, and set theoretical topology. His research is highly cited. He was founding editor-in-chief of the Semantic Web Journal, the leading journal in the field, and is founding editor-in-chief of the Neurosymbolic Artificial Intelligence Journal and of the iOS Press book series Studies on the Semantic Web. He is co-author of the W3 Consortium recommendation OWL 2 Premier and of the book Foundation of Semantic Web Technologies by CRC Press 2010, which was named as one of 7 outstanding academic titles, 2010 in Information and Computer Science by the American Library Association's Choice magazine, and has translations into German and Chinese. He is founding steering committee member of the Neural Symbolic Learning and Reasoning Association and the Association for Ontology Design and Patterns. And he frequently acts as conference chair in various functions. For more information, you can visit his website. Thank you, Pascal. I'm repeating again, we appreciate having you. Now this is your turn. Thank you for joining us, and then please go ahead.
Thanks a lot, Ozan, and really thanks for inviting me. I was actually back at Wright State University where you and I, of course, first met in person just last week, because my former PhD student and then postdoc, Kogen Shimizu, he ran 2 back-to-back conferences there. In particular, KCAP was there last week. So I was back, 6 years later at the place where kind of my US efforts really began. So and where we met. So thanks a lot. And let me just say that while I will not be talking explicitly much about neurosymbolic artificial intelligence, the work which I'm going to talk about here, and Kogen Shimizu I just mentioned is really a big contributor in this effort as well. While I will not be talking about neurosymbolic AI as such, I understand this work to be part of the neurosymbolic AI effort. So while I don't have slides for this, let me just give you a little bit of a context here. Neurosymbolic AI is bubbling right now, as you, I'm sure, are aware of. If not, neurosymbolic AI is about bringing together symbolic AI, everything that belongs to knowledge representation reasoning, and perhaps a little bit more in terms of symbolic processing. I have a rather wide perspective on this. What is symbolic? Because, well, like, term rewriting stuff is very close. In fact, I think coding assistance is also very close, because coding is inherently symbolic, and so on. Anyway, neurosymbolic AI is about bringing together the symbolic AI, knowledge representation reasoning, symbolic processing with deep learning, and more generally artificial neural networks, because deep learning is just what happens right now, and 10 years from now we'll probably have a different term for it. But the artificial neural network paradigm will not go away. I'm very sure about that. So bringing those together for mutual benefit. And one of the things about this really fast-growing area right now is that there is so much going on. It's difficult to keep overview over the different things that are being tried. A lot of the work is, of course, in terms of trying to take a symbolic system and a neural system and get them interact, work, split a task in the right way, and so on. But there's also other work, which is probably less mainstream. One is using symbolic systems to get into understanding what neural systems do, or trying to extract mostly rules, whatever other whatever other knowledge representation structures out of artificial networks, deep learning systems. And this here, which I'm going to talk about, is about knowledge graph and ontology engineering, which is inherently, as you all know, a symbolic task. It has been and still is mostly done by humans. We have fuzzy understandings what quality is, and also diverging ones often. And trying to do this with large language models is, in a sense, a neurosymbolic challenge, because you're trying to solve tasks that we humans conceptualize as symbolic, because ontologies and knowledge graphs are symbolic structures which symbolically encode knowledge. And we're trying to do that with a deep learning architecture, namely with large language models. So that's why this is in that general context. Now we're talking about that. With some examples of recent progress we have done, and they also all have to do with modularity. And I'll come to our notion of modularity, what we mean by that, and why we believe that our particular perspective here is particularly helpful, and the bit of data we already have on this. So, all right, list of underlying papers. I'm not going to go into that. I can share the PDF, but I also understand it's being recorded. All right, so knowledge graph and ontology engineering. I use this term as a vaguely defined term to describe a set of tasks central to the life cycle of ontologies and knowledge graphs as data artifacts. And really, it's not, there's no hard definition, right? But everything around that. And it has been a little bit of a holy grail, I would say, for the semantic web community to try to automate or semi-automate a lot of these things, because simply it's a lot of work. Doing this with whatever you have in mind is quality for knowledge graphs or ontologies, well, unless you have really low standards and you're not looking at reusability at all, then it's a lot of work. It needs a lot of expertise, both from domain scientists and then also from knowledge graph engineers. You need at least one person in the room who really understands logic, otherwise things go easily wrong there, and so on. So it's expensive. It's a lot of work. It's expensive. And automating or semi-automating these tasks, of course, bears the promise that you can lower the entrance threshold, you can lower the expenses, you can lower the time needed in order to do these tasks, hopefully at a reasonable level. And that has been around for a long time. And a lot of it has, let me just put it bluntly, evaded the semantic web community, even in a kind of reasonable semi-automated fashion. And it just shows kind of it's tricky. It's a tricky thing to do. Now things may be changing right now. I don't think large language models at any time will do high quality outputs automatically, but I believe that they are set to help us accelerate. Like they're set to help accelerate in so many areas of our society. Also here, they will do the same. And perhaps the analogy is very similar to what they do in software engineering, in coding right now. They can help accelerate. They can free the human from more mundane tasks, and leave the human in an area where they do the more tricky stuff, and in particular the quality assessment. And that's kind of the view I have on these as well. So, all right, let me just mention 4 particularly central tasks that are a lot of work. Ontology modeling, so constructing of a schema for knowledge graphs is one of them, and related to this, extending or modifying an ontology. is generally something that takes a lot of work if you want to do it well. Ontology population. Ontology population really refers to you have an ontology which you want to understand as a schema, and you want to construct the knowledge graph. It adheres to this schema. And by the way, a lot of what I'm saying here, if you like to do your schema with Shackle and similar paradigms, I believe things apply similarly, although that part of the spectrum isn't so clear to me. And I still think that there's a lot of things you could have done within the ontology paradigm. There was no need to make a new standard just to give the old standard a few more twists. But anyway, that's just my perspective. So I think some things carry over, although I'm not good enough to speak about which things carry over. And I'll talk about that because the ontologies and their structure will actually be central in what I'm talking about. So ontology population, knowledge graph construction, then ontology alignment, which is schema mapping in order to move data from one knowledge graph to another under a different schema, or to join them into a joined schema. That's ontology alignment. And I'll talk a little bit more about this because we have the most tangible results on ontology alignment at the moment. There's another one I want to mention, which is a little bit an other one, that is entity disambiguation, or co-reference resolution, as you sometimes say it. Essentially, with that I refer to either the situation that you have the same entity with two different names, but you don't know it's the same entity, so you want to find out if it's the same entity, or you actually have kind of the same named entity, same identifier, whatever, but they're actually different. And this is a kind of a slippery slope, right? Because if we talk about Kansas City, they can have a lot of meanings. Or if we talk about forest, then it's not clear where to disambiguate and where not. Things are very slippery. Or as linguists say, every word has a different meaning depending on the context in which it is, right? Which is, of course, a real problem for knowledge representation, because knowledge representation is kind of hard. You may say, but vectors, well, the future will be the judge to what extent vectors can really do this stuff. I think they can help, but they cannot solve it. And I have mathematical reasons for that, but I'm not going into that. All right. So automating, semi-automating has been always a key line of research in semantic web, mostly with limited success. They're hard. I mentioned that already. And in some cases, even establishing good, convincing, realistic baselines for evaluation is already hard. So that's already a problem. But you can make benchmarks, right? But benchmarks can suck as well. So and then there may be a danger sometimes that a community overfits to the benchmarks and so on. I'll come to that a little bit. So the idea here is, as already mentioned, using LLMs to semi-automate. And yes, we will look primarily at alignment as our lead example. But before I go there, I want to talk a little bit about modular ontologies in the sense in which we developed it. And that is because we believe that the way we modularize and the things we have around modularization will be key to advances in this particular field. So let me talk about modularization. The story starts actually a long time ago. And I talked at KCAP about this in my keynote, so I'm not going to repeat all that. But essentially, where this came from was from it's an accumulation of several things which were brought together. And one of the things that plays a role here are ontology design patterns, for example. There is a kind of history also of semantic web or ontology development methodologies, and we take ideas from a lot of those. The extreme methodology, which I don't like the name, Eva Blomqvist, Valentina Prasuti, and so on, is of course one of the inspirations. But I believe we went quite beyond that. And one of the key the central pieces around which we conceptualize things is the notion of module, and that kind of evolved over time. And there is a whole process around this, which is in the paper, which is listed here on the screen right now. And this is a whole ontology design process. And while this process was made for humans originally and came out of our efforts there, it has been developed from the first moment with an eye towards automation or semi-automation. In fact, the whole thing started when Kogan, as a starting PhD student, was in my office and said, "You're doing this kind of modular." We didn't call it quite modular back then, or not as systematically, this ontology design, and I'd like to automate that. And we talked about it, and in the end settled for let's try to understand the process better for humans first, and then look at the automation. As we already suspected back then, looking at this for the human was the PhD thesis, and then LLMs came around. So just in time to actually look at the automating. So it's kind of, as if we had planned it that way. All right, key ingredients. And one of the key aspects here is a divide and conquer strategy. A module within an ontology developed using this paradigm is essentially a piece of the ontology which conceptually fits together. That's the idea. Conceptually for the human expert. And an ontology consists of interconnected modules. So this notion of modern, there's others around in so many web community. This notion does not necessarily talk about kind of, finding pieces which have least connections between them, right? That's another way of modularizing, but that's actually not what we mean. What we mean is things that make sense conceptually for a human. It's also, they don't have to be disjoint, because that's not how humans think. They can actually be nested or overlapping and so on. Because each piece is how kind of what makes sense for a human. It's also a fuzzy notion, because what makes sense for a human, depends sometimes on perspective, or kind of what exactly do you include, what exactly do you not include. And we're embracing all that. We're embracing a multi-perspective paradigm. The whole ontology design methodology embraces a multi-perspective paradigm. We're, for example, saying as part of this, don't start with a definition. A definition pins you down. That doesn't help. You don't need to have a consensus around the definition before you can define a really good, a really helpful, really useful ontology for your data integration and data management purposes. You only need a consensus on the piece that you're modeling. And that can often be a multi-perspective thing. You do not have to agree on one perspective. What's, by the way, interesting, just to make one unexpected connection to LLMs, which I learned about, or actually heard last week, and it was kind of so obvious for me. We were working with historians some years ago, and I'll come to that because the enslaved ontology and system, and then we were using that as a benchmark. I'll come to that later. Our main the main people driving that, who we were working with, are at Michigan State University. I met them last week at the conferences where I was. And they gave a presentation about their attempted use of LLMs for their data management in history, so his historical data. And they said a lot of interesting things. But one of the things they said is that historians, they drive on multi-perspective. It's kind of part of how they think and do. Multi-perspective is important, but it's incredibly difficult to get multi-perspective out of LLMs, for all kinds of reasons. Yeah. They also said it's very difficult to get an LLM, tell them a kind of objective analysis of how racist the text is, because they refuse to do it, right? Which kind of is not helpful for historians. But anyway, I digress. So divide and conquer. Modules in the context of human ontology engineering or automating, semi-automating LLM ontology engineering are, among other things, a tool for divide and conquer. And human attention span is limited. An LLM attention span is limited too, as we know. Right? So the more you can focus by deciding what to prompt, the better value you get out, whether you prompt a human or a system. And if you throw several dozen classes with definitions at a human and let it do some ontology engineering, and there is no internal structure to the thing because it's just all things connected in all kinds of ways and perhaps not really well documented. That's a really hard task for human. It's the same for the LLM. We'll see that in a second. So that's all the key things what modules do here. And yes, there's other aspects here which play a role. And let me just for the MOMO paradigm, the modular ontology modeling paradigm. And really key to this is the first one here on the slide. A module is a conceptual unit in the eyes of a domain expert. That's really what it's supposed to be. And that also means that understanding an ontology can be understood, again, divide and conquer, by understanding each module often separately, and then how the modules connect. And that just helps you to focus on different pieces at the same time. And now a module is not just one class, right? It's often more complicated than that. I'll come to examples in a second. We have other things that go into the mix, and it's all in the paper. And in previous papers that led to the paper which I mentioned, there's a language for using OWL annotation properties, so you can fold it into the OWL standard to identify modules as part of an OWL file and to link to other modules and other ontologies which are related, or to ontology design patterns which are used for making your module. There's a Protege plugin which Kogan did called Commodity, which actually assists in it's a kind of prototype system to showcase assisting visually in MOMO-based ontology modeling. We do a lot of visual here. I'll come to schema diagrams in a second. We also moved from just kind of loose collections of patterns, which was what was done previously, to having ontology design pattern libraries, things that fit together, which are homogeneously defined, which come with OPLA annotations and so on. So there's a lot of things here which actually go into this, and there's also specific workflow to which I probably won't come, although I do have a slide on this later, but I may have to skim over this. All right. So early conjecture, ontology modules will not only help for humans with knowledge graph ontology engineering tasks, but also for automation or semi-automation. And that's that was before LLMs even came along. This here is a schema diagram for a little ontology we did in a supply chain context. That was collaborative work with NIST, the National Institute for Standards and Technologies. And you don't need to look into details here, right? The main piece is that this is we have these schema diagrams. We don't overload the visual syntax. Of course, you can add some things like multiplicity on the arrows, on the relations. It has these boxes as either a class or it is actually a pattern. Sorry, a module in this case. So, for example, over here would be an agent module, right? For example, or over here would be a place module as part of, and these are the gray boxes. The gray boxes are the modules which you see in a little bit more detail. So for example, up here is a trajectory module, which comes from a pattern which we did 10, 12 years ago or something like that. And of course, however you model a trajectory, I'm not going to go into this here, place and time will play a role, but here in this case, we did not even specify as part of this module how place and time should be modeled, because now you can take this and put in your own way how in your context place and time are modeled, because that depends so much on the application, for example. So in any case, you see these gray boxes, they can be nested, but they cover a conceptual unit, right, which are important for supply chains. In that case, there's events that's a design choice. The events are the things where something happens with the thing which is being shipped, which usually results in a trace as part of the ontology, right? So something's happening at some event which gives you a fix, a measured point of place and time in the trajectory. There's containers, which of course important for this. Identifiers are important, and then the notion of traceable resource unit, which comes from the domain experts. I did not know that is actually a term before I started working with these people, and that is kind of how you can understand it. Now, under all this are axioms. This is fully axiomatized. In fact, we even have a standard way as part of MOMO how we approach axiomatization, a very, very a detailed axiomatization approach. But again, there would be a separate talk how we do that and why we do that. But we're not showing those here and we're talking with domain experts really on the level of diagrams only. By the way, the open arrows here are subclass arrows. That's also why they don't have labels. All right, that's just another example. This is a kind of little that we did it for a tutorial, a kind of food example. And just wanted to share there is a little recipe ontology which we did as a tutorial. Essentially, what we want about recipes is a pre and a post, because we're not interested in modeling in this particular use case the actual workflow of the recipe, but the pre and the post is a situation. Now again, description of situations and a very old ontology design pattern coming out of I believe Dolce Light originally, which doesn't matter here. And then, of course, in that context, you may have quantities are important, quantities of stuff, of food in that case are important, and so on. The upper box here is a module for FDA nutritional information, which is on US labels. So it would be a different module for Europe, right? So now if you know where this information is, right, which gives you the nutrition label representation, and it's defined in the documentation, it's annotated in the ontology, you can just take this out, put in the European one, right? And you're good to go. If this is not identified because I have a US-centric view, right? I just make this big monster ontology and I throw this at you, then as a European, you don't even know where to start. Kind of where is this thing? You need an expert on the ontology to do that. So, and that's one of the kind of human parts where this is easier. All right. So, talked about this already. This type of modularity should help. It should also help LLMs. And I want to talk about ontology alignment as one of the tasks because we have the clearest story there. So, almost all the work on ontology alignment, and it's whatever, 25 years ago, the benchmark, which at ISWC every year, the OAI benchmarking competition runs since 2004. Almost all the work on ontology alignment has been on 1-1 class alignments. So the question, you have two classes, are they the same? And if it's a bit more sophisticated, they ask, are there subclasses, right? The two classes in the different ontologies. And that's kind of almost all the work that was done there. There was a little bit of a change on this because, of course, there is awareness that the reality is more difficult. So in the mid-2010s until the end 2010s, there was some work on complex ontology alignment, which essentially means you're looking for alignment rules like the one given here. The first line would be from one ontology, and the other two lines would be in the other ontology. And both pieces talk about project funding, research funding awards. That's from the GeoLink ontology. And what you would like to have is this type of correspondence, complex correspondence. And that's tricky, right? And one of the reasons why there was so little work on this was because even when there was a little bit of an upswing in this about 10 to 5 years ago, it essentially kind of didn't work. We made two benchmarks out of this. I'm skipping a slide here. We made two benchmarks out of real work on ontologies. We had two use cases. One was with ocean scientists. The other one was with the historians on the history of the slave trade. We had two ontology modeling for data integration tasks. And both of those, naturally, for reasons having to do with the projects, we had to actually make two variants of the same ontology. Now, there's a story in each case, which I don't need to tell you, but we kind of had to do this. And we did not have ontology alignment in mind, but we afterwards realized we can use this to make benchmarks. Natural benchmarks, because of course we knew how they relate to each other. We actually needed the relation in order to move data between them. So, and then we made these two benchmarks. And there's example rules. Well, you've seen the one, at the bottom is another one. And Wikibase is used here in the background, which is why you have these Q identifiers and stuff, which makes things even more difficult. And for one of these benchmarks, when you try to publish it, the reviewer said, this shouldn't be published because this benchmark is so far beyond anything that an ontology alignment system can do at the moment. And then I thought, kind of, okay, that's a weird perspective. Yeah, but the paper got published anyway, so that was good. But that's where we were. Yes, absolutely. The only inroads which were made here during this initial work on kind of where complex ontology alignment was looked at in more detail, were with very strong assumptions, like, for example, having a shared A box between the two ontologies. Now, that's not a realistic assumption for anything, really. But in these cases, you could do it, right? But without these, essentially, the systems are completely helpless on this kind of benchmarks. And by the way, so heavy reification is one of the issues here, but there are others. If you look at these in more detail, and of course there's more, whatever, several, they have two or three dozen alignment rules in the benchmark. They break types, for example, in many cases, right? You have rules that if you put the rules together with ontologies, you can no longer reason. So it's even difficult to argue how you actually evaluate correctness, because for that you need to do ontology reasoning. So that it's kind of, you run into all kinds of difficulties here. Also, things may just be cryptic sometimes, like at the bottom row here, EDQ 410. If you're familiar with Wikibase, then you know that's their way to have a class name, and person here would be a type of label. And in other ontologies, the label or the name of the class would be encoded in all kinds of different ways, or sometimes be several hops away, right? Which is really tricky to deal with. All right, so what did we do? First of all, we did not start by asking the LLM to make the rules. We make it easier because we have semi-automation in mind. So what we did was we gave the LLM, say, the left-hand side of the rule, and then asked it to give us the predicate names on the right-hand side from the other ontology which are relevant. Right? We did not ask for the rule, we asked for this. And the reason is that if you have this reasonably well, a human can do the rest. Yeah, relatively easily. So that kind of made sense to us as a question. And if you do that and look at it that way, then you can do an evaluation essentially using precision and recall at this stage, because you give it a left-hand side, you know you want those four in this case, as a response, and then you may get 4 or 5, right? And they may be overlapping with this. You can look at precision recall in order to evaluate that, and you can do that over all the rules. Now the story is doing this by just giving the LLM the ontologies and the prompt and the kind of asking it what to do. Essentially, just did not work at all, right? I mean, we're talking about kind of 4 or 5% correctness here, which is, of course, much too low to do anything useful with it, right? I mean, 4 or 5%, right? So it's a complete failure. And now come in the modules. And, looking at it this way, you might perhaps already understand what's going on. What we do with the modules is we focus the attention of the LLM. And, we would do the same with a human. In fact, we started designing this study for Amazon Mechanical Turk to do it with humans. That was the original idea. And then while we were doing this, LLMs hit the ground, and we said, okay, let's not even do the Amazon Mechanical Turk. Let's just throw it directly at LLMs, right? Same thing. You give this to a human, the human will be pretty overwhelmed with, several dozen classes to look at. But if you give them modules and ask first, kind of, which modules do you need to look at, then things become much easier. So here's the modules, right? At the top is a diagram of modules in one of the benchmark ontologies, GeoLink, right? So if you have a left-hand side that talks about funding awards, then you may be saying, well, I probably need to look in this module, right? Funding award. I don't need to worry about cruise or event or vessel. I just look at funding award. And perhaps, some things that are a little bit related to it, yeah, like agent role. But really, that's where I need to look. Divide and conquer. And the same for the enslaved ontology. This is the names of the modules. It's not a ton of modules in each case, right? Although the ontologies are reasonably large, they do real data integration tasks. And that's the whole idea. And you're probably not surprised that this worked like a charm. I was surprised. It worked much better than I thought. So what we did was we gave the system the left-hand side of each rule, and we gave it the list of module names. And good naming is part of Momo. right? So most ontologies I look at, I quite cringe how people name things in their ontologies. Good naming and thinking about what is good naming is part of Momo. So we gave it the names of the modules and asked which modules do you need to look at. And then the LLM told us which modules it needs to look at. And then we just fed it those modules, and suddenly it worked like a charm. And the evaluation, or a kind of a high-level view on the evaluation, is here at the bottom for enslaved and GMO. That's the two benchmarks. So remember, we look at precision and recall. Of course, okay, we look at precision recall. So recall would mean, well, a recall of 1 would mean in the predicate names the system gives you contain all the ones you actually which are actually in the benchmark for this particular rule. A precision of 1 means that all the predicate names it gives you are actually in the right hand side of the rule, right? And it turns out that you get a recall of 1 for 37% of the rules in enslaved and 45% of GMO, and we get a precision of 1 in a third of the enslaved and 46% of the GMO entities. If we lower that to 75%, it would be 3 out of 4, right? We're essentially over 50% for most of these. Yeah, and if we say half of them, right, then we're in the 70s on recall and also for precision. Now, if you just get half of these, then that is something which in an interactive system with a human should help you focus. Because you get kind of, you look at them and kind of, half of the ones you get are good and you spot they're correct. And then if you have the right interface, which can actually, guide you to adjacent pieces, you can piece together the rule, because the rule always has to do with adjacent pieces. And that's kind of, we haven't done that evaluation on the human, but it kind of seems obvious to me that if you design an experiment around it, that should work. So this worked like a charm. Right? Without modularity, not at all. With modularity, yes, it did. So, and I'm aware I have 5 minutes. So let me just very briefly talk about other knowledge graph and ontology engineering tasks which we looked at. And we have not done this stuff in as much detail, right? We haven't brought it home as much yet. But there's a little bit we've done. I believe Kogan has done. There's another paper, I believe, which may not be listed here, where he's advancing on this. Don't have time to look at the Momo workflow. Really encourage you to look at the paper if you're interested in our notion of modularity. So one of the things about this, about now looking at other tasks, not the alignment tasks, but for example, looking at ontology design task, is we need really good and comprehensive ontology design pattern libraries in order to do this. You need quality libraries. And of course, you can do this by, just if people would just make their ontologies, and when they make their ontologies, I believe they have in their minds already what the modules are in these ontologies, because you think about the related things, right? You think about a key notion which you want to model. It's just that it often gets lost once you kind of put it into a monolithic ontology, and then a monolithic documentation which focuses on classes and their relations, right? And then I look at these documentations and I say, why are you not telling me what was in your brain, right? So it would actually be easy. And at the same time, whenever we model ontology, we make good patterns out of it as well, which are generalizable, right? Because it's easy when you do ontology modeling. I hope more people would do that, because it would be easy to make these pattern libraries. But we don't have that really. We have pattern libraries. We have some patterns which are more helpful, some which are a mess, and you need to curate that. So, but in any case, one of the thoughts, of course, is also, can we use LLMs to make something like micro patterns, simple patterns that are still helpful? And we have one paper which looked at that first, just for common nouns in the English language. And what we see is encouraging. This would be something essentially not much curated, right, around the notion of air and relevant aspects for the notion of air. And that works good for some contexts, at least, I think. And of course, this is too much. It's just star shaped. Most notions are much more complicated, but it's a start, right, to kind of get there. I don't have more on this, right? But I want to talk also about ontology population, where we have a little bit more done. We went back again to the enslaved ontology, which is this ontology on the history of the slave trade. And there is a hub. Just go to enslave.org, and you're in the data hub there. There's also a in the background, it runs Wikibase. You can actually look at the Wikibase data there as well. And it integrates several databases on the history of the slave trade. So we use this for us as a benchmark for ontology population. The problem here is that we needed a modular ontology, right, to benchmark our approach, and all kinds of other benchmarks we have for ontology population, they don't have modular ontologies underneath them. But here we had a modular ontology. How did we make a benchmark out of that? Well, the enslaved.org hub focuses on people related to the historic slave trade, the transatlantic slave trade. And a lot of these people, well, not a lot, look at it from enslaved.org, but still a considerable number of these people actually have Wikipedia pages. So, and that's what we used. We took the Wikipedia texts and then used LLMs to fill our ontology with the corresponding triples. And since we had the data, the structured data on the enslaved.org hub, we could look kind of how well that went. That's essentially the idea. And yeah, we had to work with some text summarization here because the Wikidata texts were too large for the window. But of course, we could drive the summarization using the modules. So essentially, we use a module. We were interested about family relationships of this person, and that means we give the LLM a focus, right? It's like you have the question in mind, and you go through the text as a human, and you dig out only these pieces, and that helps because it's a conceptual unit. What we do. So we had to deal with that. We used some text summarization techniques there, and then of course we also use that to in the end. So we use that as a kind of cutting down, right, of the big problem, divide and conquer, in order to get our triples. And we used a lot of different variants here, different approaches to this. And we used both of the ontologies, which are in the alignment benchmark, because you have two ontologies here. One is the Wikibase based one is the other one. And there's a lot of data here we can talk about, but just to say, the exact variant didn't matter that much. We got into roughly kind of 75–80% correctness here using this modularization as the key driver of what we were doing here. And that's incredibly encouraging. Of course, that's just one first study. We have to do more. We have to look at other pieces. Well, the problems is the lack of well-modularized ontologies, right? But this is clearly encouraging in that particular direction. All right. So it's 9:45. So conclusions. I believe LLM-based or assisted, I really want to call it assisted, knowledge graph ontology engineering is very promising and exciting direction. And there's, of course, a lot of work going on here, and I only talked about my own. We posit that modularity may be a key ingredient because you need to find ways to divide and conquer. And, other notions of modularity may be helpful as well, as long as there are modularity notions that actually help cutting the problem down into pieces that correspond with human conceptualization. Why? Because LLMs have been trained on human texts. Yeah, so they capture human conceptualization. That would be kind of my driving premise here. And I just also want to kind of put the view a little bit differently, because sometimes what we do in the ontology world and knowledge graphs world is we take the paradigms that come to us and then we try to make things work using these paradigms, right? Whatever, RDF and OWL, right? Or whatever, property graphs. It may behoove us to also think the other way around and think, how can we improve these standards in order to make knowledge graph and ontology engineering tasks work and easier? And here's one proposal, right? When you do your modeling, keep modules in mind, because you're doing it anyway. You just need to kind of be aware that you do that. You think of conceptual units, and then put them both in your documentation and in your OWL file, because it goes such a long way in helping humans and systems, right, to help with all kinds of ontology engineering tasks and knowledge graph tasks that need to be done. All right, that's the last thing I wanted to say, and yeah, we have 10-12 minutes for questions.
Thank you very much for your talk, presentation, and I ask the others, please ask questions or type them into the chat, and then we will ask. Yes, Raza, please. Hello, we don't hear you. And Eleni?
Yes, thank you very much, Pascal. Very interesting talk, and also very nice to see all of this neurosymbolic aspect, let's say, on ontology engineering. I know some people are not very fan of it, but you're saying that maybe we should use them in cooperation with humans, so maybe that's what it's tackling there. I would like to understand a bit more about the models, because in the past there used to be all of these ontology patterns. So I would like to know how they're different and how also you assess the quality.
Yeah, so let me put it that way, because I think that's perhaps the perspective which is most helpful. What's the difference between a module and a pattern in our conceptualization, right? How we understand it, and essentially, kind of we started with patterns, right? And we kind of thought of an ontology as composed of patterns, right? So you connect the patterns, and then we noticed that's actually perhaps not the best way to think about this. And we needed another notion, and then we started calling it module. So what's the difference? In our mind, in how we use the conceptualization right now, a pattern is a standalone thing that generically models a certain human conceptualization of a notion. And a pattern is usually multi-perspective, and it should, in our opinion, be designed in such a way that it rather errs on the side of being too comprehensive. Also, it should be kind of at the fringe. It should be open. It should not kind of, if you model a trajectory, then of course place and time play a role, but place and time should be different patterns in their own right. And when you model a trajectory pattern, you should not pin down what you mean by place and time, because that makes it too singular as a pattern. So you kind of leave those open. So in that sense, a pattern is not an ontology, because you would, for example, in a trajectory pattern, just have a hook for here goes a place pattern, here goes a time pattern. Yeah? And you make them in such a way that somebody who wants to model, say, a trajectory can take the trajectory and leave out stuff and instantiate some patterns and make some minor changes and quickly comes up with a really good model for a trajectory. That's, for example, what happened here, right? This is actually a very, very trimmed down version of what our trajectory pattern actually looks like. It has very few pieces of the trajectory pattern, but it has the crucial pieces and still adheres to the same mindset and can easily be linked with other concrete instances of the ontology design pattern. So that's a pattern. Now, what's a module? A module is a piece of an ontology. A module lives in an ontology. A pattern is standalone. A module is a part of an ontology which encapsulate human conceptualization of a notion specified for this particular need in this ontology. So what we have here is the trajectory module. It has been done by using a trajectory design pattern as a template, as a rough template, I should say, to instantiate this module. But this module here is very concrete, because if you use it as part of an ontology, then as part of the ontology, and to make it useful as an ontology for a graph schema, you have to say what you mean by place or by time, right? Like, do you mean Lang-Lott coordinates, or do you mean place descriptors, or do you mean references to a certain geoinformation system, right? Or standard names or Wikipedia pages or whatever you use to identify your places. The places can be very, very complicated. But if you use it as a concrete ontology for a concrete use case, you have to specify this. And that's the key difference is why I use modules versus ontologies. Versus ontology design patterns. So thanks for the question. I think that's a very important point here.
Just if I get it right, if I may have a follow-up here. So the patterns are, if we could say, much more on a higher level, while the module is closer to the instances.
You could say it, put it like this, yes. So an ontology design pattern does not. You should usually not be able to use an ontology design pattern directly as a schema for your knowledge graph, because it will be open at the fringes. And also, it will usually contain things you don't really need in your particular case, right? Although particular use cases will leave out different pieces of this, right? For example. So like, for example, one of the things we left out here is the notion of segment. A segment is how you travel from one measuring point to the next. That's a segment, right? And for this particular case, it didn't make sense to represent those, so we left them out, right? For others, it may be important how you got from A to B, for example. By the way, your question had a second one, and you were asking about quality. How do you assess quality? And this is good. Yeah, it's a very, very critical piece. And I do not know how to assess quality. I know that quality is important. And I know that different ontology engineers, different people working with ontologies and knowledge graphs have different understandings of quality. I believe the only way how to really do this these days is to look at the use cases, but it's a very, very, very limited perspective. I think that in the end, what is extremely important, to come back to the original semantic web vision, is you have quality if what you're doing is easy to reuse for adjacent or new contexts. Because that's the original idea, right? Easy to reuse. It goes both for the graphs, and that's where linked data failed. A lot of linked data failed. But also for the ontologies, and that's where a lot of the ontologies failed as well. Although for both of them, that was part of the original plan. You make reuse easier. Yeah. Now, my claim is that you should not reuse a whole ontology. You should reuse modules, if at all, right? You may only want to reuse patterns. Even trying to reuse a whole ontology, in most cases, even if it's a good ontology, may cause you more work than it's worth it. Because every ontology is always singular, right? But most of them are. There are a few exceptions, right? Because they have conceptually for completely different purposes. But the patterns are not, right? They are made for multiple use cases. And I believe for reusing knowledge graphs, it has a lot to do with making the ontology more accessible. When if you have a modular ontology, for example, then your knowledge graph naturally falls into modules adhering to the pieces of the ontology, which are patterns, right? You can extract your trajectory graph if you know where the trajectory module is in the schema. And I believe that should help a ton as well. But, the work is out there. Other than that, I believe the ontology community has to talk more about that. One of the difficulties with the reuse paradigm as a quality measure is that assessing that is extremely costly. Because for that, to really validly assess whether you save work by reducing a previous defined piece of ontology engineering, you would have to compare it with not reusing it, so doing it from scratch, and you would have to have a large enough problem to do the assessment. And that's kind of a problem because you are asking for whatever $1 million project funding twice just for the value of assessing. So I think that's tricky. However, here's the thing. I don't know of any study that ever brought home in a kind of, stringent assessment that object-oriented programming is superior to what was done before object-oriented programming. So why is it a prominent paradigm, right? Because people started using it and they feel it's helpful, right? And they notice it's helpful and they oh yeah, that helps, right? Because it again, chops things in the right way. So we should probably keep that in mind as well, that not everything needs a formal evaluation. It just has to make conceptual sense, and people have to feel it helps. And here, it's completely feelable that it helps. Long answer to the evaluation question.
Thank you.
You have a question from Huan Yu?
Thanks for the presentation. If I remember correctly, at some point in your slides, you mentioned giving definitions of concepts and the relationships may be not the focus at the beginning of the design process. So my question is, what's your suggestion, like at which point we give definitions, and what if these definitions may influence how we think the module structure?
I would say just stay away from definitions. Just stay away. I know I'm a heretic in certain ontology circles if I say that, but I really say stay away from definitions. So very briefly, how do we approach this, right? In the end, it may be difficult. It may be different if you stay, say, in some science domains, right, and stay within the science domain with notions that are well understood, and have clear scientific definitions. And then there is no harm in working with definitions, of course. But to be honest, that's not the really interesting modeling domains for me. It's also not the complicated ones. I've been working so much with geoscientists and now with historians, right? Kind of, or even, try to, what's a water column? What is a forest, right? I mean, there's papers on defining what a forest is. If you go into history, things get even more difficult. And as mentioned, historians thrive on multi-perspective. They want that, right? So what do you do instead? What do you do instead is you essentially do what logic tells you anyway, right? If you use logic as a paradigm here, which in ontology modeling we often do, logic cannot capture definitions. Every axiom is just a restriction on the set of models that actually fits your logical axiomatization. So the only thing you could do is restrict. You usually cannot define, right? That's just not the right mindset, in my opinion. And it's also not the right mindset for doing, for example, ontology merging or multi-perspective, bringing databases together, because databases are developed with certain things in mind, and you cannot presuppose that you can find a consensus definition that captures both databases. I think that's preposterous, right? So what do? You find a consensus restriction. You find a model that works from different perspectives. And the way we approach this is not by asking definitions. We still ask for key notions that are important for the domain that we're interested in. We're asking for key notions, and then we're trying to develop modules, usually out of design patterns, for these key notions, which work from multiple perspectives. We're not asking well, we may ask at some stage, what is for you, right, a trajectory or a water column? But in the end, if we have different people in the room who differ on what it is, we're not asking them to find a consensus on how they define it. We're trying to find a model that works from both perspectives. And that's a different mindset in approaching it. And, if you ask me, that works like a charm. And I believe that this approach also gives you a model that works for other perspectives as well, without people having to buy into your, sometimes narrow definition. Of course, you can also say, well, that just boils down to make a vague enough definition. But really, if you make vague definitions, then why make definitions at all, right? And I think the key here is the change in mindset. And yeah, there's probably a lot of discussions that could be had about that. So I'm completely aware of that.
Thanks.
All right. I believe we're at the end of the time, and I need to actually hop out because I need to transfer to another meeting, which I can't miss. So, but thank you everybody for being here. And if you want to follow up and have more questions, then please don't hesitate to to email or contact me on the Neurosymbolic Slack or elsewhere.
Thank you very much for having you today. It was really interesting. Just we can have a few minutes for the assembly if some members want to stay because we have some news. And Pascal, have a very nice day.
Thanks a lot. I'm trying to find out how to stop screen sharing and I'll hop out. Thank you very much and feel free to follow up. Thank you.
Thanks
Bye-bye.
very much. Have a nice day.
Thank you.